Syzygy, episode 22. How do you measure a universe? And welcome back for another edition of the Syzygy podcast. This is episode 22, and in this episode, we're going to be talking about how big everything is. Or rather, how do we know how big everything is? We get very used to, in discussions of astronomy, saying, well, we know how far away the moon is and the sun is, and it's, the sun is 8 light seconds away, and we know what that means, down to very fine fractions of a meter and so on. But how do we know? How do we know how far away the nearest star is, or the nearest galaxy, or the other side of the universe? How do we know this stuff? Because it may be news to you, but you can't just stick out a ruler and tap it on one end and tap it on the other end and measure it. That doesn't work. So at some point, you need some other methods. And here to help figure all of that out is my podcaster in crime, Emily Brunsdon. Emily, welcome to the microphone.
Hello, hello.
So how do you measure a universe, Emily? How are we going to start this? I'm guessing that there's more than one way to do this.
There definitely is, because it turns out it's an insanely difficult thing to do. It's probably one of the most difficult things astronomers try and get up to. And it's so important that I've actually built my entire first year teaching of astrophysics around this exact question.
So welcome to Astrophysics 101. Let's talk about measuring things. Which, I guess it makes sense, doesn't it? If you're going to start doing more than just pointing at the sky and saying, what's that? You're going to need to start talking about where things are and how they're put together and how they, how they're formed. What does a galaxy look like? How does a galaxy form? How do clusters form? And to do that, you need to know where things are.
Yeah, and we had a great question from one of our listeners actually about this.
Kicked all of this off. So one of our listeners and friend of the podcast, Chris Baker, wrote into us through Facebook, facebook.com/syzygypod, and asked, look, he said, when researching the distances of the objects I photograph, because he's an astrophotographer, and quite an amazing astrophotographer. We'll put a bit of a link to his stuff in the show notes, because Chris is pretty awesome. He said, when researching the distances of the objects I photograph, I'm surprised by the variations in figures and uncertainty. For example, I saw recently M109. What's M109?
It's a spiral galaxy.
Spiral galaxy. M109 is 84 million light years away, give or take 25 million light years. So 84 plus or minus 25 million light years. And that's a big uncertainty. That's saying anywhere between, say, 110 and 60. That's a big range.
That's approaching 30%, right?
Right.
Yeah.
That's a big range there. And so why is there such an uncertainty? And even backing one step back from that, how do we even know that number in the first place? And so that kind of kicked us off for this episode, saying, that's a really good question, Emily. How do we know where things are in the sky? I'm guessing, correct me if I'm wrong, but I'm guessing that the first things that we figured out the distance scales of were the things closer to home, like the moon, the sun, the other planets. Is that right?
Yeah, that's definitely true. And there were lots of really genius ways that ancient astronomers came up with for how to measure the distance to, say, the moon, based on things like shadows, how far the Earth was from the sun, based on how much of a shadow it casts with a stick at different places. I mean, these are clever people that came up with this stuff.
The more you think about it, I mean, the moon always, to me, feels like it's just there. It's up in the sky, and it's you could almost touch it. You could almost reach out and grab it. And it's only when you see just how far away the moon is, it's like 20 Earth diameters away. It's a really long way away, that even just measuring the distance to the moon is a non-trivial feat. Like, well done. So doing that was done long time ago with shadows and sticks Greeks and angles and
yeah, it's fantastic. But of course, we've developed techniques to today.
We've moved past sticks.
We've gotten there. But it turns out there's no one technique that we can use to measure every object in the universe. So we actually have a kind of a suite of techniques that we use depending on what the object is and how far away it is.
Okay. I mean, I guess that kind of makes sense, because we don't have, things here on Earth, we don't have the same tools to measure distances at all scales. You can't use the same tool to measure how far is it from one end of the United Kingdom to the other end of the United Kingdom as how big is an atom. You can't use the same tool for that. You've got a whole bunch of different tools which overlap, and you can sort of check them as you go along. Astronomy is the same, I'm guessing.
Exactly,
Right.
yeah. And so we've actually constructed this whole thing we call the cosmic distance ladder.
Right.
Which is basically, if you imagine a ladder, every rung in that ladder is a different technique that we use to measure a different distance out there in the universe. And we're very, very lucky that quite a lot of these techniques overlap. And we actually use that for calibration and
Right.
making sure we're kind of doing an okay job.
Yeah, when a new rung on the ladder comes along, you need to be able to check to make sure that, okay, we can figure out what the distance is, but how do we know we're right? Well, we know we're right because we can check it with this other way that also works in this particular case. So we can measure the distance to, for example, this star with the new way and the old way and make sure they agree and calibrate them
Yeah,
that way.
that's right. So we maybe have on the order of about 20 different techniques that we use in modern astronomy. But I think we'll restrict ourselves today to talking about probably what are the biggest 5.
Okay, we'll do our top 5 today.
Yeah.
Okay, and are we going to work our way out in distance?
Yes,
Starting
yeah,
close to home?
Because
Okay.
that also turns out to be how we work our way out in accuracy for the
Okay.
most part as well.
Okay.
So if you think about the things in our solar system, well, actually, we can make very direct measurements of things like planets in our solar system because, well, we've been to most of them.
Well, that's true, actually. Yeah, we've visited them and we know where they are. Having said that, it's not quite the same as going out onto the footpath with, did you ever in school have one of those, it's a wheel on a stick and it
yeah,
clicks? What are
yeah.
they called? Measuring wheels or something? I
Yeah.
can't remember. But you wander along when you're in about grade 5 and click, 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 and it's a meter or a yard or whatever it is in your particular local system. And you measure the size of a tennis court or something, right? It's not quite like that in visiting Mars. It's a little bit more
Yeah.
like you send a robot out with one of those wheels on a stick and does it for you. But how do we know that that's right?
So we're in communication with these satellites and probes and so on that go to different places in the solar system, and we can do one of two things, but they're based on the same principle. Really, we can either measure how long it takes for a signal transmitted from a particular satellite back to us. We know what speed that signal was traveling at.
Right, speed of light. And we
Speed
know
of
that
light.
one pretty well.
We are very, very good at measuring that. So we know the distance, basically. And in a very similar vein, we can also, for some types of objects, so long as they're kind of quite solid, we can bounce radar signals off them to work out their distance, which is a very old technology that we've been using for 100 years now.
And radar, once again, I mean, it's the same kind of stuff. It's light or radio waves. But you're firing those out from the Earth and waiting for the signal to bounce off and come back to you. And you're measuring, again, time of flight.
Yeah.
So whether it's a signal from a robot over at Mars coming back to us, or whether it's literally bouncing radio waves off an object, it's still using the speed of light and the amount of time to tell you how far away the thing is.
Yeah.
To a high degree of accuracy. How far away can you get with the bouncing off with the radar?
Pretty far, really, because you're not limited to how bright an object is so much. So what we can actually measure the shapes of things like asteroids, even some of the things that are way out beyond Neptune.
Wow.
We can bounce things off, signals off them and
That's
get
got to be
returns.
a really, really weak signal by the time it comes back. You know,
You need a really big radio telescope to collect
Wow.
it back again. Yeah. The only unfortunate thing with radar is that you can't. It's very difficult to bounce it off surfaces that are not really solid. So, in terms of distance measurements, we don't use radar so much for the sun and for Jupiter because they're a bit kind of gassy. We do use it in other contexts of those objects, but in terms of distance, getting to what is actually the surface is a bit inaccurate.
Yeah, I mean, the sun looks like a fairly well-defined ball in the sky, but where the sun's atmosphere, if you like, begins and ends, it was over a very, very large distance. So
Yeah.
where does the sun stop and space begin? Not so clear.
No,
And
so
radar
that would be
doesn't
too
work.
much error for basically. So we use telemetry more in modern times, which is this measuring of how long a signal takes to get from a particular spacecraft to us. And you can use that to actually work out things like the distance to the sun because we kind of know the geometry of our solar system. So if you know where most of the things are in our solar system very accurately, you can work out where the other things are.
Right, you sort of reverse engineer it and say, well, if all of these are over here, then let's draw that on a piece of paper and work out the angles and distances and so on. And so the sun is there.
Yeah.
Fantastic.
And the most recent measurement that is accepted in the astronomical community for this, I can give you this in an exorbitant, wonderful detail.
Okay, go on then.
This is 1 astronomical unit, the distance between Earth and the Sun.
And that's the average distance of the Earth to the Sun.
It's a type of average based on our weird and funky orbit.
Right, okay. Weird and funky average, yep.
Yep. It's 149.597870700 times 10 to the 9 meters, so billion meters.
Wow. That's really accurate.
It's really accurate.
That's not mucking around.
And wait till you hear the error on this one.
Plus or minus.
0.0000003.
Wow.
Which works out to be 3 meters.
Wow. So we know the distance on funky average of the Earth from the Sun down to 3 meters.
Down to 3 meters.
That's like less than the length of your office.
It's so cool.
Good work, astronomers.
Yeah.
And that's through the equivalent of doing a bunch of geometry and time of flight measurements for light signals, radio signals, that kind of thing.
Yep.
Wow. Okay.
So we're pretty good at that measurement.
Yeah. Well done.
Nailed it.
Well done. So that's number one.
Yeah.
Okay. So we're working our way out through the distance scales of the universe. That's the first rung on the ladder.
Yeah.
Okay.
Now let's think if we wanted to apply that technique to something like a star,
Okay. Yep.
another star.
So you said a minute ago that we can do that all the way out, even sort of, past Neptune, we can still do these kinds of measurements. And so the next rung out, I guess, is the farthest flung reaches of the solar system and then out into the next star. So where does it give up?
The next star is just over 3 light years away from us. So if we wanted to do radar, let's say we could bounce it off the surface and fairly accurately, we'd have to send the signal. It'd take just over 3 years to get there, another just over 3 years to get back again. That's a long time to have to wait.
So that's 6 years return. And then add in the fact that you just said a minute ago that the whole radar bouncing off idea doesn't work so well for stars anyway.
And it gets worse than that because you lose the strength of your signal for every meter that it travels because it's spreading out over space.
Yeah, you've got this big sort of cone of radiation going out and this tiny thing at the end of it, which is then going to bounce off and another big cone coming back towards you. And the amount that you're getting by the time it comes back is ludicrously small.
Yeah.
So even possible in principle?
Well, I mean, it's hard to say never, but
Never say never, because someone's going to turn around and go, we just did it.
Definitely impractical at this point.
Yeah. So that's not the right way.
No.
So what is the right way? How do you measure the distance to the nearest star?
So we've got a really nice technique which actually uses the fact that we orbit around the sun.
Okay.
And we can try a little experiment here. Okay. So you can put out your thumb at arm's length.
All right. Everyone at home,
Yep,
thumb at arm's length.
And if you close one eye and look at where your thumb is against the background of whatever you're looking at.
Yep. I've got it lined up with your window.
Okay. Now open that eye and close the other eye.
It's moved.
It's moved.
It's not in front of the window. Oh, I like that. Okay.
Yeah, so this is something called parallax, which means that if you make a measurement of something from 2 different directions against a background that's further away, then you can actually tell that it's close to you. You can tell your thumb is closer to you than the background of the window, for example.
Because the background, the window is moving in my field of vision depending on which eye I've got open. And my eyes are a few centimeters apart, and so there's a different angle going on there as I'm lining stuff up.
Yeah.
So you said you can use the fact that the Earth's going around the sun. So Earth on one side of the sun is a very long way away from the Earth on the other side of the sun in its orbit. So you've got 2 different positions in space.
Yep.
So
you can measure close stars that are close to us. You can measure them move, just like your thumb moved, against the background stars that are further away from us.
Oh, okay. So you still need something much further away, which, like the window here in the office, I'm assuming isn't going to move, isn't going anywhere. But the difference in position of the Earth's place in its orbit around the sun, one side or the other, gives you that parallax effect.
Yeah.
That's clever.
And this is actually how we define the unit that we use mostly for measuring distances to stars, which is a parsec. Because basically we said, well, okay, how much do you need to move by 1 arc second? How far away is that object if it moves 1 arc second? Which is
hang on, remind me what an arc second is. An arc second is a 60th of a degree.
Yeah.
So you've got 360 degrees in a circle, and then each of those degrees, even more finely grained, you break up into 60 arc seconds.
That's right.
Right.
So it'll be like a 60th of a second in time. So so how far away is an object if it moves exactly 1 arc second in the sky? And that turns out to be a distance of just over 3 light years, which is 3.086 times 10 to the 16 meters.
Right. So parallax allows us to figure out how far away the nearest star is, stars which are reasonably close to us, things which are reasonably close to us, because you need that background.
Yeah, you need to be able to measure
compare
a
it
difference
against.
basically in the
Yeah.
position. In traditional astronomy, that was the background of stars that were further away, but we've now moved into doing even more precise measurements, and this is particularly where Gaia comes in. So the spacecraft Gaia, we launched in 2013. The kind of headline mission, if you like, of Gaia is to measure the positions incredibly precisely of 1 billion stars
Wow.
in our galaxy. So what it's going to do is basically over 5 years, it's going to take 70 measurements of every star, of those billion stars. It's actually more than that in total. But the billion, we really are the ones we want to nail the distances to very, very accurately.
And I assume in being able to do that, that then allows you to build a really good 3D map of the galaxy with 1 billion stars in order to learn about the galaxy.
Yeah.
Because it's easy to forget that when you look up at the night sky, it looks like all of those stars are in the same plane. They're just on the dome of the sky. But of course, they're not. It's all 3D. You know, what we see as a constellation isn't a flat thing at all. Those stars are all sorts of different distances away, and that's what Gaia is measuring.
Yeah, that's right. And it's ultra precise. So we're getting to a level of precision with Gaia that we've never had with ground-based observations before, because there's no atmosphere wiggling the stars around. We've got this very, very uniform instrument that's measuring the same thing over and over and over again. So we're looking at getting a precision in the position of these stars, which is it's quite cool. It's called astrometry rather than astronomy, astrometry.
Astrometry, measuring of distances. Yep.
Yeah. So we're looking at getting a precision of this, which is on the order of 20 micro arc seconds.
That's 1/1,000,000th of an arc second. That's really small.
It's really, really small.
That's really small.
To try and give you an idea of how small that is, if say the astronauts who visited the moon, if they left behind kind of the user manual for Apollo 11 or something like
so
that.
big chunky manual left on the surface of the moon.
Yeah. So if they left behind that and we were looking at it from Earth and we could see this manual, it would be the same size in our sky as a full stop at the end of a sentence in that manual.
So you're not. I thought you were about to say. So it'd be like the size of the front of that manual. No, you're a full stop on the end of a sentence.
That's
so
a micro.
A full stop at the end of a sentence on the front page of the manual on the moon is the precision to which you could measure.
Yeah,
this
some of these
parallax
stuff.
in the sky.
So that's 1
That's
micro arc second.
staggering.
Amazing.
Wow.
Amazing. So cool. So
Okay.
Gaia is a huge hero of astronomy, and it's doing a fantastic job. And we've had data already come out of it that have just been mind-blowing from that.
All right. That's very cool. Well done, Gaia. So this is rung 2 on our 5-rung ladder that we're going through.
Yeah.
This is the parallax method, measuring distance to things which are relatively close by. So let's just make sure we understand relatively close. We're talking nearest stars through to stars throughout our galaxy. How
Yeah.
far can you use the parallax method?
You can use it quite far, but the errors start to creep in, right? So the nearest stars, they're going to have 20 million stars in the Gaia survey that they're going to have a distance of less than 1% error in those measurements, which is pretty amazing.
That's pretty good.
Less than 1%. That's pretty good. If we're talking about the things that are distance of about the center of our galaxy, that creeps up to about 10%.
Right. And what's the biggest factor in that uncertainty? Why is that getting so big?
Because the further away you are, the smaller you move, if you like, between
Right.
those 2 points.
Right.
So the fractional error on the measurement itself starts to creep in.
Right. The equivalent being, if you hold your thumb out, the closer your thumb is to you, the more it appears to move across the background of the room as you close one eye and open another eye. The further your thumb is away from you, the less it moves across that background. Yeah. And so the bigger your uncertainty in that measurement. That makes sense. Okay.
Yeah. So Gaia can do stuff that's outside the galaxy as well, but of course more and more errors start to creep in at that point. But that's pretty good. We can get stars that are let's say, in our half of the
Yeah,
galaxy.
so we can
pretty
map out our half or our quarter of the galaxy, and then assuming that the galaxy is at least reasonably symmetrical, you then say, so our galaxy looks a bit like this. Okay, great. So that gives us galactic scale. So what's the next rung? How do we get out to the edge of our galaxy and beyond?
So those are kind of two very direct and very geometric measurements of position. After about the edge of the parallax that we can do, it's we have to use indirect measurements and kind of use models or kind of equations that we've developed to help us understand other types of measurements and put these into context with distance.
All right, so what sort of thing?
So this is where we start to hit the realm of what we call standard candles. So we look at the light coming from objects, and if we know how bright that object is, then we know how far away it is.
That's a lovely name, standard candle. And the notion being that, let's say we had here on Earth candles which were all made exactly the same. And if you lit one, you knew how bright it was really well, then you could put that candle here in the room and you could see how bright it is. You could put that candle a fair way away, across the other side of a field. It would be much dimmer because it's further away. The light's spreading out in a big sphere and you're only seeing a little bit less of it. You know how bright that candle is because it's a standard candle. And so you could use the dimness of that candle to tell you how far away across the field that candle is.
And we could even go modern and say, let's call it a 60-watt light bulb, right?
Okay. So the standard 60-watt light bulb,
very
except that more romantically, standard candle. That's nice. So we're obviously not using 60-watt light bulbs or wax candles in space. So what's a standard candle in astronomy?
Well, this is where it gets hard. There are things that we know the brightness, the luminosity of reasonably well, but it's hard. Actually, we don't know the distance and we don't know the brightness very, very accurately. And this is where things start to get a bit funky. But there are some things we know moderately well. So one example, and the first example that helps us overlap with parallax, is Cepheids. So these are types of pulsating star where their brightness changes over time. And we've been measuring Cepheids for 100 years or so. They're brilliant. They're brilliant objects. I love variable stars. So what we found out was that their period of pulsation, so how long it takes them to go through a cycle of going bright and going dim, is actually dependent on how bright they are on average.
Okay, so you've got these stars which just naturally are variable. They're getting brighter and dimmer and brighter and dimmer and brighter and dimmer at a very regular rate?
Yes, yep, very, very regular.
And the period of that, how quickly they're brightening and darkening, you're saying depends on how bright they are generally anyway. And so you've got that relationship. You know that if you see it wiggling away, doing its brightening, darkening, and you can measure that time period, then you know how bright it is. And then that means you've got your 60-watt light bulb. You've got your candle.
Yeah.
Right.
So it turns out that the ones that vary the fastest are on average the brightest. And so we have a relationship. We went out and measured lots and lots of these Cepheids, and we're able to draw up a relationship that says, if you see a Cepheid that has this period, then it's going to be this bright intrinsically.
So does that mean then that if you want to measure distances out beyond where we can use parallax, you can't measure the distance to any arbitrary object in the sky? You've got to be looking for these specific kinds of, as you said, this one example, the Cepheid variable stars. You've got to be looking for those and finding those, and those are your candles.
Yeah, because if you just go to any old random star, you don't know how bright it is itself. So if it's a very, very bright star and it looks bright, if it looks, medium brightness in the sky, that probably means it's quite far away. But if it's a very, very faint star and it's medium brightness in the sky, that probably means it's very close.
Okay, so these Cepheids, are they the only kind of candles we've got?
They're not. We've got quite a few. And so most of the types of observations that we do outside of our galaxy fall into this kind of basket, if you like, of standard candles. But if we come back to M109,
Right,
at this
which was
point,
from our question from Chris Baker. 'Cause
Yeah.
he was saying, what did he say? That he had seen that it was 84 million plus or minus 25 million light years, which is a big uncertainty range.
Yeah. So let's think about where that plus or minus might have come from. So we can construct this relationship between brightness and period, and we have a benchmark set of Cepheids that we use, which are the Cepheids in the Large Magellanic Cloud. So they're in this little dwarf galaxy next to us.
Right, yeah, because our galaxy, the Milky Way, it's got a couple of these smaller dwarf, sort of blobby clusters of stars orbiting around it, the large and the small Magellanic clouds.
Yes, yep. And they, in that cloud, the conditions in that cloud are kind of similar to how they are in the Milky Way. So we know roughly what the properties of these Cepheids are. And so we can compare them quite well to our ones, and we can make that calibration, if you like. The problem is when you start to measure Cepheids in other galaxies, they might be a bit different to the Cepheids in our galaxy.
Yeah, you're making the assumption that what's further away is the same as what's close to home. You're making the assumption that these are standard candles.
Yeah, and there's lots of factors that mean they might be a little bit different. The stars themselves might be a little bit different. They might have different chemical elements in them. So they might
have formed it in different ways.
Yeah, pulsate a little bit differently just because the temperatures might be slightly different from these different chemical elements. Or what else is really hard to measure is actually how much light do you lose in between us and that object. So there's stuff in the universe.
Right, because it's dependent on, I can see my candle out there across the field, and if I can see how bright it is all that distance away, and I know how bright intrinsically this thing is, then I can measure the distance. But if it's a foggy day, if there's something in the way, then that candle's going to look even dimmer, and I don't even necessarily know that. I don't know that there's something in the way.
Measuring the amount of fog is really hard, really
okay.
hard. So I had a look at one example of a galaxy that we measure using Cepheids. It's NGC 4258, which was quite famous just about in 2000 because it was one of these galaxies that started to make us change our calibrations a little bit, basically. So we had two distance measurements for this galaxy. We measured one really accurately using masers, which is a technique that we're not going to talk about today, but it's kind of, you can use radio techniques to measure these masers.
A maser is a type of astronomical object.
Yeah,
it's a thing.
It's a beaming of radio basically towards
right.
us. And then got a measurement of 7.2 plus or minus 0.5 million parsecs.
Okay, 7.2 plus or minus 0.5.
Yep. That's cool. And then we go out and measure the Cepheid distance, and we get 8.1 plus or minus 0.4.
Okay, those don't overlap.
They don't
7.2,
overlap. Not with the accuracy that we're claiming we can make with these measurements, which is a bit of a pain. And I looked up this because it was super interesting for once you get into all the reasons for the different uncertainties.
Digging down into the detail.
So digging down into the different uncertainties, there were about 7 types of systematic and random uncertainties that were already being accounted for.
Right.
13 different values that they put into this work.
So these calculations aren't just, here's the measurement and it's about this. These are, here's the measurement and then we've taken account of this and this and this and this and this. We've figured this one out and we've made an assumption about this and we're pretty sure about that and here is our answer. Like these are very detailed
Very detailed, yeah. And what we sort of concluded was that actually maybe our benchmarking from the Large Magellanic Cloud wasn't as good as we thought it was.
Wow. So you're comparing this against things which you're pretty sure you know. It turns out maybe not so much.
Yeah, which means you there have to go recalibrate all of your other measurements that you've ever made with
everything.
This. Yeah.
Wow.
And it has impacts on other distance measurement techniques that we use because we use multiple different types to calibrate each other.
Wow, that would have been a big day. Yeah. By the way, everyone in the astronomical community, we may be out by a few percent. Yeah. Big deal.
So errors are really, really important. And that's just one example of how we made a kind of measurement that needed to be corrected and correct everything else as well. So Cepheid measurements on average, I guess this is not even an average that I've calculated, it's just kind of me looking around at different galaxies we've measured using these techniques. You get kind of errors in the order of tens of million parsecs.
Okay, but how does that work out in terms of, say, percent? Like we're talking 1%, 10%, fraction of a percent?
Tens of percent, 25%, kind of that level.
And so that's where Chris Baker's question comes in, which is he's being surprised by seeing the galaxy M109 being 84 plus or minus 25 million light years. Like that's about 30% or more uncertainty. That's really, really big. But this is why.
Yeah, exactly. And I looked up actually where those measurements came from for that particular number for 109. Turns out there's about 26 different measurements we have made of M109.
So 26 different measurements. And how well do they agree?
Well, this is
to within 30%.
Well, this is kind of where that number comes from, because we've used about 4 different techniques to measure the distance to M109, and most of them are kind of at tens of megaparsecs and uncertainty. So if you kind of add, it's like the very basic error analysis that you can do is kind of add up all your uncertainties and divide by how many measurements you've made, and you can kind of get a rough idea of maybe how accurate that is. It's not statistically, the best way to do it, but
isn't that amazing though? Because all of these objects we can see really well. You can get really good images of them. I find it amazing that something that we can see so well, we still have such a big uncertainty about where it is. Anywhere in this particular case, this particular example, anywhere from 60 to 110, almost a factor of 2 million light years away. That's a massive uncertainty. But we can see it. It's that.
Yeah, there it is. And we're so reliant on these kinds of objects having things like Cepheids in them, because if they're not, then we have to use other techniques, or it gets really hard. So M109, for example, I didn't see any Cepheid measurements for. What I did see, though, was a quite cool other type of measurement that we use, another standard candle, which is that of supernova. Now, supernova are great because they're insanely bright. I once had someone ask me, would you rather have a nuclear bomb go off next to your eyeball or have a supernova go off at the distance of the sun?
Oh, well, I mean, I'd rather neither of those. Thanks very much. But if I have to make a choice...
Go for the nuclear bomb.
Really?
Every time.
On your eyeball?
On your eyeball.
How? I mean, it's a moot question, because either way you're toast. But
no matter what people ask about supernova, they're brighter than you dare to hope.
Take any other option. Yeah, fair enough. I mean, and I remember reading once, they outshine the entire host galaxy.
Yeah,
in terms of brightness, which is one exploding star against billions of not exploding stars, and it'll outshine it for a period of time. But how can an explosion like that be a standard candle? I mean, that's just a massive, blooming great explosion.
Well, there's a special type of supernova called Type 1a, not very excitingly
well
named.
Well done again.
But the way we understand these particular supernova explode is that you always have the same mass when you explode, because it's a critical mass. You build up a mass up to this point, and then you blow up.
Okay,
basically.
so this isn't just a star deciding to go kablooey just at random. This is a very, very finely tuned. When we get to this point, then it's really clear what's going to happen. It's going to go boom, but in a really, really consistent way.
Yeah, so we do have supernova that just go off in random things, and we don't know how bright they are intrinsically. But this one specific type always explodes at this exact same mass.
Gee, that was lucky.
Yeah. It's great.
I mean, it didn't have to be that way, did it?
Oh,
but
no.
That's nice.
So Type 1a supernova are super, super important, because we know what their maximum brightness should be intrinsically.
And as soon as you've got that, as soon as you've got this really consistent, we know brightness of this thing, then all you've got to do is wait for a Type 1a supernova to go off, which I'm guessing isn't happening in the object that you're looking at just when you need it to happen.
No, you do have to wait.
Yeah.
But the good thing about looking at several hundreds of billions of stars in a galaxy at one time, you've got reasonably good odds, right?
As I remember you saying many podcasts ago, in astronomy you get used to looking at lots of things that happen very rarely.
Yes.
In order to actually see them happen.
Yeah, you can always win out with looking at lots of things if you're looking for a rare
and if you're looking at a galaxy, you've got lots of things.
You've
got billions of stars.
Things, yeah.
How often, here's a question for you, how often does a star go kablooey in a galaxy?
Well, we reckon a supernova generally will go off in our galaxy, for example, once every 100 years or so.
That's still not often.
It's not super often, and it might not be a Type 1a, But at least, if you're looking at thousands of galaxies.
Yeah. So again, you wouldn't be looking at a particular galaxy and going, come on,
Yeah.
supernova, come on, because that's very unlikely. But if you're looking at lots of galaxies in a bit of the sky, and there are lots,
Yeah.
there are lots of galaxies out there, then you're waiting for one to go off, and it shouldn't be too long.
No, we detect
That one-
hundreds
that
of
one there.
supernova every year
Right.
in the universe. So,
Okay.
this is okay.
And so as soon as you've got one of these type 1As, you can go, right, bang, we now know, at least to within some accuracy, where that is.
Yeah. I mean, one very impressive example is in the Virgo cluster. We have some galaxies there. We got Cepheid distances to some of them, which kind of give us 15 to 25-ish million parsecs away. If we get a type 1A supernova, we've got that down to 19.9 plus or minus 5.
That's pretty
Point
good.
0.
That's pretty good.
So, you start to get a handle on actually we can do this a bit more accurately sometimes with supernovae.
Okay. So this is still all in this third rung up the ladder, isn't it? This is all still standard candles.
Well, we're up to number 4.
Oh, we're up to number 4.
Supernova. Yeah.
Supernova, okay.
Yeah.
But it's a variation on a theme.
Yeah,
So we
yeah.
had standard candles in terms of variable stars. Now we're up to supernovae as another type of standard candle.
Yeah.
Okay. And how far away can we see?
Well, the great thing
Supernovae.
about supernovas is they're quite bright.
Yeah,
so
I mean,
we can,
outshining entire galaxies. If
Yeah.
you can see a galaxy, you can see a supernova.
exactly. So we got a good handle on that. But we, as you say, we haven't got every galaxy having supernovas going off in it. Some galaxies just are not going to have many going off at all because they're really, really old and there's not much exciting.
Not a lot going on.
Stars blowing up in the galaxy. So so it's we can go very, very far away because they're very bright, but we do need other techniques as well to go even further. So this is where we come down to the 5th one.
All right. So what do we got?
So this is Hubble's law.
Hubble of the Space Telescope, but of course, that's named after him, not the other way around.
Yeah, Hubble of the astronomer,
Yes.
who the Space Telescope's now named
Yes,
after.
but people might have heard of the Space Telescope. Is my point.
Yes,
Is my
yeah,
point.
yeah.
So Hubble's law.
So Hubble's law looked at how basically if you can measure how fast things in the universe are moving towards or away from us quite accurately.
Okay, how does that work?
So we have the Doppler effect, which is when things are traveling towards you, the light kind of all bunches up, which makes that object appear bluer than it should. And when it's traveling away from you, the light kind of stretches out, which makes it appear redder than
This
it
is
should.
the light version of that that you hear when something passes you at high speed. As it's coming towards you, the sound is higher because all the waves are bunching up, and that's a higher frequency of sound, so higher sound. As it then passes you, and down to the bump the microphone, down to that lower pitch, because as it's past you, the sound waves are being stretched apart, and that's a lower pitch. The equivalent with light is red light and blue light.
Yeah. So we noticed reasonably early on in our first measurements of things outside our galaxy that everything seems to be moving away from us.
This is like 100 years ago. Right?
Yes, yeah.
And everything's moving away from us.
Now, it's not because we kind of smell bad or anything like that.
But it must have been a bit of a disturbing discovery. Hang on, guys, there's a problem. No one likes us.
No, it's really not. It's not us, honest. No, it's big. It's just the geometry of the universe. And if you sit in any galaxy in the universe, if that universe is expanding, then it will appear to you like every other galaxy is moving away from you, no matter which galaxy you sit on.
But that was the big question, wasn't it? This was some of the earliest evidence, or the earliest evidence, that actually that is the case, that it's not just a static universe, and so you would expect some things to be coming towards you and some things moving away, or everything staying still, that everything moving away from us means that the universe is expanding. And so the only way that you can make sense of that observation, of Hubble's observation, is that, wow, the universe is getting bigger.
Yeah. So
Wind that one backwards and you've got a big bang, and that's a topic for an entire other podcast. But
It is.
here we are. We live in an expanding universe, which means stuff's moving away from us.
and we can measure that expansion. So we started measuring it off, and we use some kind of they're useful units for astronomers. They might be a little bit weird units for other people, but basically we have something called the Hubble constant,
Right.
and that tells us if you know the speed of something, a galaxy. Like this only applies outside of our galaxy. It doesn't apply in our galaxy. But if you've got a galaxy that's being carried by the expansion of the universe away from us, then if you can measure its speed, then you can work out its distance, because we know that for every megaparsec that you move away from us, so every million parsecs, then your speed will increase by around about 70 kilometers per second.
So the way to think about that, I guess, is we're talking over these very large distance scales of, between galaxies, very big distances. Then if it's the space itself that is expanding, then the more space there is, the more expansion you've got. So the further away something is, the more space in between, the more that's expanded, the faster away that thing seems to be going. Something close by, not much space, so it's not moving away from us very, very quickly.
Yeah.
But it doesn't work for things close by because there's lots of other stuff going. Like within our own galaxy, gravity is a much bigger thing.
Yeah, gravity messes up Hubble's law.
And so there's going to be stuff moving towards us and past us and over us and away from us and in all sorts of different directions. But when the expansion of space is the big thing between galaxies, that's where Hubble's law comes in.
Yeah, and it's great because once you have that measurement, then you can say how fast the universe is kind of expanding, right?
And you measure speed how?
And you measure it via this, how fast these galaxies are moving away from us from the Doppler shift.
Right. Okay. So you're looking at the light and coming from these galaxies, and you're saying, hang on, the light has been Doppler shifted towards the red by this amount, and that tells us how fast this thing is moving away from us.
So we know, for example, hydrogen has some very clear spectral lines. It's kind of like a fingerprint. When you see that, you know that particular feature. You know it's hydrogen. You know in the laboratory it should be at this color. It's just kind of a little bit red usually. And then if you see it super, super red, that particular feature, then you know that galaxy is moving away from you very quickly.
And there's a lot of hydrogen in stuff in space. So hydrogen's an easy one to measure. And so you can see the shifting of that fingerprint to tell you quite accurately, or reasonably accurately, how fast this thing's moving.
So here's where the kicker comes in.
Right. There's always one.
It's very hard to work out exactly what the Hubble constant is.
Okay, so we've got this really nice law that says the faster you are, the further away you are, except that it's not really particularly well measured.
Yeah, so the number I said, we've got about 70. We've been measuring this for 80 years or more. And we've got numbers that range anywhere between 50 and 100, maybe 100 and a bit.
Right. So that's a big uncertainty.
It depends what you measure, what direction you measure it in, what other factors you take account of.
So they're all consistent in saying, yep, the universe is expanding, just not quite sure how quickly.
And of course, we've tried to nail this down, right? So actually, Hubble, the Space Telescope, one of its key mission goals in the early 2000s was to do just this, figure out the Hubble constant.
Okay, and how'd it go?
Not too bad. So Hubble, it had this, it was called the Hubble Key Project, right? In 2001, published this value of 72 plus or minus 8.
72 plus or minus. Well, that's not bad.
Kilometers per second per megaparsec.
When you consider what it's trying to do, that level of uncertainty seems reasonable.
Yeah, well, but except that's a more than 10% error. And when you translate that into things like how the universe is expanding, how old the universe is, because if you know how fast it's expanding now, and you can make a fairly-ish rough statement that it's kind of been accelerated, or it's been traveling at that velocity for the age of the universe, then actually you can just
wind
divide
that clock backwards.
Yeah, you can have 1 divided by that number and you can get the age of the universe.
Right.
And this is actually the back of the envelope calculation we have for how old the universe is.
And so if you do that, you do 1 over and you end up with, what is it, about 13.6 billion years? But if you've got about a 10% uncertainty, then that's
quite a few billion years.
Yeah, that's 13 plus or minus a few billion years, which...
And then, okay, we know now that, of course, the universe is not just it's not just expanding. It changes the rate at which it's expanding over time, which is really confusing, but we talk about that, I think, sometime. We also don't really know if the Hubble constant is constant in time as a number.
Yes. Is the Hubble constant even constant?
Has it always been this number? Was it a different number in the past? Or is the Hubble constant different in different directions in the universe, depending on what's there?
So if you factor all of these things in, then this highest rung on the ladder, it's amazing that we can do it at all, but there's still a big uncertainty
It's
there.
super uncertain, yeah.
Yeah, but we can use that to get out right out to the very edge of the observable universe.
Yeah, so some of
I mean,
the
that's
furthest
what gives
things
us the
we can
observable
see.
universe.
Exactly. So quasars and so on, right on the edge of our observable universe, we can see and measure using this technique.
So we've gone all the way from bouncing radar off the moon right out to the edge of the observable universe in 5 jumps.
Yeah. The important thing is where those 5 jumps overlap. And that's where we've got to be really, really careful and use each of the techniques themselves to measure the distances to the same things and calibrate. And it's this ongoing process of calibration that we need to do to refine these measurements. So because of that, a lot of our future distance measurements, whether we're developing new techniques or whether we are refining techniques like the use of Gaia, for example, Gaia is going to have a huge impact on our ability to measure the distance objects within our galaxy and even to calibrate the Cepheid scale. We're going to be able to do that with Gaia. And so the future for these kind of distance measurements is a tightening up of all the things that we have and also using wonderful new techniques to be able to put in there and increase that overlap and increase the precision of that calibration.
That's it for another edition of Syzygy. My name's Chris Stewart, and we've been producing this episode, as ever, here in Emily's office at the University of York. Emily, you're the Twitter queen. If people want to get in touch with us, how do they do that?
Twitter's so easy. All you need to do is go to @SyzygyPod, SYZYGY, and you can find out all the things that pique our interest over the weeks and also get an early alert as to when the episodes are going up.
That's right, because, I mean, we get to talk about whatever topic we decide in any given week, but there's a lot more astronomy than that going on. A lot of things just fly by us and we grab onto them and throw them up on Twitter. Also up onto Facebook. You can go and search Facebook for the Syzygy podcast and you'll find it. That's how Facebook works. And go and sort of give us the Facebook thumbs up and give us a like. Or, as our friend of the show, Chris Baker, did this week, send us a question, make a comment and say, hey, you guys should do a show about this. And look, we did. So thanks for that. That's really cool. Failing that, you can also just go to our website, syzygy.fm, and go and find the form on there to get in contact and just say, hey, love what you guys do. Why don't you do a show about this? And we'll give it some thought. You can find us on YouTube as well, if you like watching while you listen. All of the shows are very visual. There's always some really good graphics, so we throw those up on YouTube as well. Very exciting things coming our way very soon. Coming up in the middle of November, we've got Your Night.
Syzygy Live.
Syzygy Live. And we're based in York in the UK. And if you are based in or around York, or you feel like travelling to come and see us, then the University of York runs every year a night of research stuff, talks and activities and all sorts of things about research things that are happening in and around the York area. And we're going to be a part of that. We're going to be doing a live show all about one of our favourite subjects, exoplanets. So come and join us for a very special live show. We'll be having a chat about all the latest research on exoplanets, taking your questions, having a natter, and just really enjoying the fun that is astronomy. It's going to be great
and
fun.
Chris told me today you might even have a special treat for our audiences.
Don't give away, but I might be bringing my guitar. You never know. Going all Chris Hadfield. So that's on Saturday the 17th. At 4:15 in the afternoon. But look, if you want all the details, go to our website, syzygy.fm, and check them out there. And if you can make it along, we'd love to see you in the audience. But if you can't make it along to see us, we understand. People listen to us from all over the world. We've got people listening in Australia, in New Zealand. So if you can't make it along to Syzygy Live, join us next time when we're back in a week or so for the next episode of Syzygy, where we'll be talking about some other awesome astronomical thing. So we'll catch you next time.
See you later.
Bye-bye.